Suppose the wheel is rolling without slipping. Find the relative velocity of point A with respect to point B. Let's first see what rolling without slipping is. If your vehicle is stuck in mud and you step on the gas, your wheels would rotate but the vehicle wouldn't move forward. That is slipping. On the other hand, if you are driving on ice, even if your wheels are not rotating, the vehicle would move forward. That is skidding. Right? So if 1, 2, 3 and so on are infinitesimally small points on the wheel and K, L, M and so on are infinitesimally small points on the surface, during skidding, when the wheel doesn't rotate but the vehicle moves forward, the same point on the wheel comes into contact with multiple points on the surface successively. On the other hand, when the wheel is slipping, the wheel rotates but the vehicle doesn't move forward. So the same point on the surface comes into contact with multiple points on the wheel successively. K comes into contact with 1, 2 and 3 and so on successively. Now rolling without slipping is between slipping and skidding. In the sense that when the wheel is rolling without slipping, at t equals 0, 1 comes in contact with K, the next instance 2 comes in contact with L, the next instance 3 comes in contact with M and so on. There is a 1-to-1 correspondence between the points on the wheel and points on the surface. This is a very laymanish way of understanding rolling without slipping, but then for a rigorous treatment we will need to use angular displacement, angular velocities and so on, which we won't get into right now. Now if our wheel is rolling without slipping and it has made one full turn, B would have gone around the center one full turn, right? So B was initially here, it would have come back to its bottom position. Let's say D is the total surface length that came into contact with the wheel during this motion. The total wheel circumference that would have come into contact with the surface is 2 pi r, right? Because B has made one full turn, so a whole circumference would have come into contact with the surface. So the surface length that came in contact with the wheel is D and the wheel circumference that came in contact with the surface is 2 pi r. Now since there is a 1-to-1 correspondence between the points on the wheel and the surface, there is one point on the wheel for every point on the surface, and so D must be equal to 2 pi r, right? Now during the same time, C also has moved by a distance of D, because here also C is on top of B, here too C is on top of B. So this displacement is D. If the time taken is t, then the velocity of C, which is given as v, is equal to d by t. But d is equal to 2 pi r, so the velocity of Cv equals 2 pi r by t. We found d to be equal to 2 pi r. Now during this time, let's try to find out the speed of rotation of B around C. The time taken is t, and B has traveled a distance of 2 pi r because it has covered the entire circumference once. So the speed of rotation around C is 2 pi r by t, right? But 2 pi r by t is nothing but v. So the speed of rotation of B and A around C is v, right? B and A should have the same speed of rotation, otherwise the wheel would get distorted. In other words, VBC is equal to VAC equals V. The speed of B with respect to C is equal to the speed of A with respect to C, and that's equal to V. However, the directions are different for A and B. A is going towards the right and B is going towards the left. Let's say the right is the positive direction. So A has a velocity V and B has a velocity minus V. VAC is V and VBC is minus V. So now it's straightforward to find the relative velocity of A with respect to B. VAB is VAC plus VCB. We can do that, right? We can introduce an object in between. If you knew the velocity of A with respect to C and the velocity of C with respect to B, you can find the velocity of A with respect to B as VAC plus VCB. But we also know that VCB equals minus VBC, because the velocity of one object with respect to another object is the negative of the velocity of the other object with respect to the first object. So VAB is equal to VAC minus VBC, and we know the values of VAC and VBC. Put it here, we get VAB equals 2V. Relative velocity of A with respect to B is 2V in the positive direction. Now just for fun, we can also do it by using a moving reference frame, as you saw in one of the earlier problems. Let's say we make our reference frame move right with a speed v. Then all the objects in the systems will have to reduce their velocities by v. So C's velocity becomes 0 in the new reference frame, and the surface velocity becomes minus v in the reference frame, in the new reference frame. Right? Then the argument is quite similar. Let's say B makes one full turn, and during that time P has moved forward by distance d. P's velocity is v, right? So v equals d by t. That is clear. P's velocity is v because the surface is now moving left with a velocity v. And since the distance traveled is d in time t, v equals d by t. So the surface length that has come into contact with the wheel is d, and the wheel circumference that has come into contact with the surface is 2 pi r, because B has made one full turn. And since there is a one-to-one correspondence between the points on the wheel and the surface, 2 pi r must be equal to d. Right? So we saw that 2 pi r equals d equals 2 pi r, but d by t is v. So 2 pi r by t equals v. But 2 pi r by t is nothing but the speed of rotation of B around C, because in time t B has traveled the distance of 2 pi r. So the speed of rotation of B around C is 2 pi r by t. In other words, VBC is 2 pi r by t. VAC is also equal to 2 pi r by t. But 2 pi r by t equals v. So VAC is v and VBC is minus v. Again, because A and B are traveling in the opposite directions. And then using the same set of arguments we used earlier, we can find VAB equals 2 times v.